before I dig into this, I wanted to be the cool teacher and show some videos. So I'm going to stop sharing this slide here for a second. I see a question. Jeff Ward, where are you in development of this aircraft? So we've been running what's effectively a 30-person R&D program for the past couple of years. And we've advanced into the preliminary design stage. And what we're doing now is we're conducting a significant fundraise that we expect to take us through completing the preliminary design, onto doing detailed design of both prototype aircraft and starting the certification track effort in parallel. And then we'll be feeding more flight test information from the prototypes into getting our certification track articles, in shape, and bringing up our production line and going to LRIP. So, if everything went perfectly, which it probably won't, but if everything went perfectly, we'd see entry into service in late 2024. So let me show you a video of what it looks like. I'll show you some X-plane simulation videos and one prototype flight test video here. So I'll start with the service video. Pull that up. There we go. So this is Manhattan to Boston. It is a commercial, so forgive me, but you also get to see all phases of flight, what it'll actually look like.
Peter, we're not getting the audio on that. Just a heads up. No.
What are you seeing?
We were seeing the video, but not the audio that time.
Oh, you weren't getting the audio. Rats. All right, let me restart. Oh, it's because I had share sound on. Turn that off, and let's try again. I'll start already in progress here. So that's what it would look like to fly from Manhattan to the end of the Fish Pier, which happens to be owned by Massport, by the way. And I've already talked to them about operating off the end of the Fish Pier. So we hope to make that happen. Oh, and Jeff said he was getting audio. So that's interesting. I've had this problem where people have said if I share audio, they don't hear it. And now Jeff says he does hear it. So I'm sorry for the technology glitch.
Interesting.
Yeah. But let me share. I want to share another one that will show you the actual fifth scale in flight test. So this video I'm going to show you, I may skip through it a little bit because it's a bit long. It shows each maneuver from two views because this was a flight test. So you'll see it from a fixed camera and then from a roving camera view. And what this test was about was maneuverability testing in helicopter mode. We wanted to see whether the handling qualities that we projected from the design and from the X-plane simulation actually played out with a real flying aircraft. And again, this fifth scale is way big enough so that with appropriate mathematical corrections, we can derive real data about how the full scale will fly. So let me show you that. Just wait to see which screen it is.
And Peter, while you're looking at that, we do have a question where your flight test operation is.
It's based out of Carlisle, Mass. So just 2 towns over, on the far side of Hanscom from me in Lexington. So yeah, we're headquartered up here right around Concord, Carlisle, Lexington. We've got a cadre of people in Connecticut, the Nutmeggers, and then a host of people across the world, really, consulting, contracting, and advising us. This flight test I'm going to show you took place in, this was in Acton, in a pumpkin field in Acton after the harvest. So, here's my zoom. Sorry for the delay. There it is. Okay, so there's takeoff. There's the same takeoff from the other view. All of this is real time, by the way. That's testing pitch authority using the tail fan. Turn the music down a little bit. Now we're going to fly backwards and test some pitch authority. So that's a horizontal turn using the flaperons deflected in the slipstream. So there's that turn again. I like the music, but I think my talking over it might be more interesting. So that was a left roll, and it started moving pretty fast. It has great authority in roll. And so there was a right yaw turn to a right roll. And so this looks like it might be slow motion, but like I said, this is all in real time. And the way it yaws is that the trailing edge devices, which would be ailerons in airplane mode, we refer to as flaperons because we use them as both ailerons and flaps. And in helicopter mode, when you deflect them, they generate yaw. And so here, I'm the test pilot for this. And so here I am flying backwards. And then we pitch forward to arrest the backwards motion. And the pitch moments are all coming from a fan in the tail that I mentioned. So the fan blows up or down as necessary to generate downwards or upwards pitching of the nose. And here's a landing. So it's a little faster than I wanted, so I caught it. It's actually a pretty good landing, if I do say so myself. One of the things I realized about landing, if you blow a landing, even after great flight, it's like telling a joke and blowing the punchline. It just takes all the fun out of it. So here's the second flight. So take off, get a little bit out of the camera. And now we're going further downfield this time. There was a little bit of a wind, so what you saw there was me to yaw into the wind so I didn't get blown into the trees. And if you see standing down at the far end, there's a safety officer. That's Dick Gersh, who I'm sure a bunch of you know. So Dick is part of our program. And we've really benefited from his expertise from his Terrafugia time. All right, so we went downfield. We're doing a turn to come back. It's 270-degree right yawing turn. A little bit of pitch forward to catch some back momentum to the right that built up during the turn. And now we're going to do a little bit of a test of how maneuverable is it. So pick up some speed going forward. And then we're going to do yaw, roll, and fly around the corner here. So here's yawing sideways. Going to roll into that. See how fast it accelerated? It's like, whoa, better tilt the other way, pull the nose down, come around the corner. Yeah, when you've got both props, it doesn't take much roll tilt in helicopter mode to develop quite substantial translation rates with sideways speed in less geeky jargon, which is great actually for, again, technical terms, gust rejection. But because we have a lot of roll authority, if we get hit by a sideways gust, we can roll the aircraft into that gust and maintain positioning quite well. Maybe not exactly as well as a high-performance helicopter, but pretty close. And certainly well enough to meet the ADS 33 handling qualities tests that people use to assess the handling of rotorcraft. And so now I'm backing up and coming towards the fixed camera. So I'm backing up and actually translating right to starboard because I didn't want to land in some rotten pumpkins. So we're coming back, stopped going backwards. Now we're just going straight down. And there's the touchdown. And again, I thought this was a pretty good landing. The gear on this version of the prototype, by the way, are two 1/3 scale Piper Cub main gear linkages. So we've got them from a big giant scale Piper RC model. So we've got another question from Jeff. How does the tail rotor change thrust direction? Variable pitch, yes indeed. Which in the rotorcraft world we refer to as collective. But yeah, the propeller in the tail can rotate almost 180 degrees. So it can blow up or down, or sometimes we like to say that the tail fan both blows and sucks, if you'll pardon the language. So we're almost to the Q&A period, but I have one more video I wanted to show you. And that is one of the reasons we know this design is going to work is that back in the 60s, there was a bunch of research on tilt wings. And the most successful tilt wing aircraft was a Canadian aircraft called the CL-84. And it had a very similar plan form to the Vy. In fact, you could really think of the Vy as the ultimate evolution of the CL-84, but we just get to benefit from over 50 years of technology advancements. So we've got higher temperature coatings for jet engines, better turbine blades, so much better power to weight in the jet turbines, so we can be one instead of having to have two like the CL-84 did, and the whole airframe parachute. But beyond that, computerized flight control systems. People have sort of feared tilt wings because one of the barriers to adoption they ran into in the 60s was achieving acceptable handling qualities through all phases of flight, including the transitions to and from airplane and helicopter mode. And we supposed at the beginning of this program that with computerized flight controls and individual actuation of all the control surfaces, again, the technical term for our aircraft is that it's over-actuated, because we can generate rolling or pitching or yawing moments using multiple control surfaces. So as you saw in helicopter mode, for roll, we actually use the propellers. With the electric aircraft, we speed one propeller up and we slow the other one down. With the full scale, we'll have collective pitch, adjustable pitch propellers, and they'll generate more or less thrust, and that's how you get a rolling moment. But in airplane mode, we use the ailerons for rolling moment, just like a normal fixed-wing aircraft. And in between, you have to go from one to the other, and it's called blending. And that the way you blend from one to the other turns out to be a trick. And it's a trick we've spent years mastering. And in the process, we've invented some new ways of controlling a tilt wing that were never done before and are only possible because of this individualized flight control. But what I'm going to show you now is a little video I did where I took one of the standard demo videos that was shot in the late 60s of the CL-84. And I flew all those same maneuvers in our X-plane simulator just to demonstrate that our simulated Vy can do everything the CL-84 did. And as it turns out, it's going to be more. So let me share that real quick here. And then we'll take questions. I reused some of the same music.
With the wing tilted up, the power lever is advanced to make a vertical ascent to hover. As in all modes of flight, the aircraft is controlled by the stick, rudder pedals, and power lever. To fly sideways, the stick is moved sideways to command differential propeller pitch instead of aileron, as in conventional flight. The 84 can fly sideways up to 35 knots. To rotate the aircraft, rudder pedal movement controls the flap aileron, which, being immersed in the slipstream, provide the necessary yawing moment. This transfer of control authority is obtained by means of a mechanical mixing box in the control circuit containing a series of cams which rotate with wing tilt. In this way, a given control input is translated to a command to the relevant control function. A thumb switch on the power lever selects wing tilt angle. Here the wing is tilted beyond the vertical to put the aircraft into reverse flight while the fuselage remains level. The 84 can fly backwards at up to 35 knots. The ability of the aircraft to fly sideways and backwards is a measure of its ability to perform hover turns in a wind while remaining on station and handle crosswinds during takeoff, transitions, and landings. 0 to 100 knots takes about 8 seconds. The flying demonstration concludes with an inbound transition to a hover landing. The relative movement of the horizontal stabilizer with the tilting wing is clearly seen. A small reduction of power is required to complete the landing as the aircraft enters ground effect.
All right.
Peter, we've got a couple questions.
Excellent.
What does the dead man's curve look like for Vi while in helicopter mode?
That's an excellent question. So for those not familiar, the dead man's curve, or less sensationally termed the HV diagram, the avoid area of the HV diagram, which stands for height velocity, is it's a curve in the POH for every single engine helicopter, as well as most multi-engine helicopters, because most of them, depending on their loading condition, will also have this. And so by avoid area, it's a range of forward airspeeds and altitudes that you want to stay out of, because if you lose an engine at that, you're going to crash. And if you crash high enough, of course, people may die. So, for example, the Bell 407 has an HV diagram that at max gross sort of intercepts zero airspeed at 800 feet. So if you're in a hover below 800 feet in a Bell 407 at max gross and you lose the engine, you may well crash, and it could be severe. So the Vi has a similar shaped HV diagram in that we want to stay low while we pick up speed, and then once you have forward speed, in the case of a helicopter, you can translate that into a chance for auto rotation, where you can use the descent of the aircraft to spin up the rotor, and then you can turn that rotor RPM into some last-minute thrust and cushion your touchdown. With the Vi, since with a parachute, forward motion actually helps us with extracting the parachute, which does two good things for us. It absorbs energy that doesn't have to be dissipated by the aircraft structure on impact, and it also orients the aircraft in a predictable way so that we know what the load paths will be when the aircraft crashes. And we're designing the aircraft structure to dissipate that energy just like your car does. In fact, we're using a lab at Kansas City University that actually is the world leader at doing this sort of structural deformation simulation analysis, along with BRS to help us do the structural design for that. So what else we got, Keith?
We also had a question regarding how does the parachute deploy? I know you covered it briefly, but if you could do it again for us.
Oh, absolutely. So Boris Popov at BRS came up with this concept, and from the beginning they've used rockets to deploy the parachute. So if you look at a Cirrus, on the empennage there's a panel, it turns out. It's painted over, you can't really see it. But there's a panel that gets blown out, and a rocket emerges and pulls the canopy up, where on the standard original version of the BRS parachute, the moving air, the aircraft moving through the air, would inflate the canopy. Now, they've actually announced, 2 years ago now, they announced a new variant of that where they use pyrotechnic inflators, similar to the inflators for airbags in cars. And the importance of that is it takes a bit of time to get the canopy inflated, and you're getting drag that whole time, which is helpful, but you really want the full canopy. And so the pyrotechnic inflators help with that. We don't have a hard number for you yet as to how low we could successfully deploy the parachute, but it's below what the old school SR-22 numbers were, which were somewhere around 1,000 feet of AGL. So it should be well below that.
Oh, that's interesting.
Yeah.
Next on our list is, can you describe what the controllability post-engine failure might be? Given the ballistic parachute system, will there be no flying it back to the ground?
Oh, that's an excellent question. And so it turns out that it's very important under Part 23 that after an engine failure, you can conduct continued flight to a safe landing, is the regulatory language. And then when you go and look into what that refers to, it's really controlled flight to a safe landing. And so there are two ways that we can have controlled flight under canopy, or two aspects to controlled flight under canopy. So this is not your standard cirrus, which really does just descend in an uncontrolled way. So it turns out that if you tilt the wing of the Vi backwards, actually I have my briefing stick Vi, if I hold it in front of my face, you'll be able to see it. If you tilt the wing of the Vi backwards like this, which we can do, we can go to 110 degrees of tilt, so it looks like that, and the aircraft is descending under canopy, the uprushing air generates forward thrust, right? So the air is hitting the back of the wing, and the aircraft wants to fly forward. We have emergency battery power. All of our flight controls are electrically actuated. So if we lose main turbine power, we still have actuation of the flight controls. And so we can still use the flaperons to steer the aircraft. So we've got, now we can point it and steer it and fly it under canopy. So that will be a controlled descent, under control of the pilot. The other aspect is if the wing was frozen, say there was damage and you couldn't tilt the wing, the canopy itself will have panels in the back of it that pop open, and the air flowing out the back of those will also generate forward thrust. So either way, we'll have forward thrust and steering. So the loss of the engine alone will still allow for a controlled landing.
Jeff asks, do you have a sense of what the max forward speed to hover transition time will be?
Yes. So I have done, so you saw those X-plane simulations, and we've benchmarked those against state-of-the-art. I mean, X-plane is a game, right? But it turns out that its physics model is quite sophisticated. In fact, I hosted Austin Meyer to present on the physics of X-plane, hosted by the Vertical Flight Society. And so if you're interested, you can go read about it. And what all the pros said, they're like, oh, it's a panel model or a strip model, where it's computing real physics. So you obviously can't believe it by itself, but when you add in other analyses and our flight tests with the real prototypes, we understand where it's telling us the truth. So it is in fact telling us the truth about how fast the aircraft accelerates and how fast it'll go through the transition. And I can tell you right now that from starting hovering over the numbers at 2.9, by the intersection with 2.3, we're fully transitioned and going over 150 knots.
Definitely impressive.
Yeah, I mean, way more than you would use with passengers. That's the peak acceleration longitudinally during that transition is 1.75 Gs. So you're feeling, 1 3/4 your own weight slamming you back briefly during that transition. So we would never do that in a passenger flight. But it is a very high performance aircraft. I mean, that's one of the fun things about a VTOL. It has to have a greater than 1 thrust to weight. And when you start using that greater than 1 thrust to weight in airplane mode, it'll outclimb any terrain. It'll climb straight up.
One of our longtime members showed up a little late this evening, and he's just asking if you could quickly describe the powertrain.
Absolutely. So the powertrain is a turboshaft engine, which is mounted here, abaft the wing. It's a turboshaft, so it has a 20,000 RPM rotating shaft coming out of it. That shaft enters a main T gearbox. So basically, you get a drive shaft out each side, so it looks like a letter T. So there are drive shafts that run down each wing with appropriate hangers and flexors and stuff to deal with the wing bending and changing shape for temperature and all that. And then we've got a planetary gearbox in each nacelle. And that planetary gearbox is the L gearbox, so the PGL gearbox. And that turns the corner up to the propeller drive shaft. And the prop is mounted to the nacelle, so all the load paths go through the nacelle. So that drive shaft is a torque-only drive shaft. So it's not taking any of the loads, bending, tilting loads from the prop on it. And then up into the propeller hub, and it's a fairly standard propeller hub, variable pitch propeller hub design. So it's a turbo mechanical drivetrain. Those gearboxes are not pushing any state-of-the-art we're lucky to have attracted a gearbox guru to do the design for us, a guy named Bob DeRusso. Bob was at one point in his career recruited by NASA to head a R&D committee about pushing the state of the art of helicopter gearboxes. But these are much simpler than what helicopters use. So, and much lighter, by the way. If you did a 600 volt electric system to distribute the power, we need most of a megawatt out of each propeller. If you did a 600 volt system, just the copper wiring in one wing would weigh more than our entire mechanical gear train. You have to use really big, heavy copper wires to send that much power around, as it turns out.
Ken asks, what are the attachment points for the parachute, and how does the parachute deploy helo versus airplane mode?
Well, so the attachment points, there'll be 2 of them forward of the wing tilt and 2 of them aft. They use Kevlar risers, and they're designed to be thick enough so that if a propeller blade struck them at full power, the propeller blade will break. The risers will not be parted. So that's safety. That's another safety measure. You know, they're to hard points on the fuselage, and all the load paths have to be. We haven't finished the detailed design on that yet, but you know, it's a very solvable problem. Cirrus has done this now. I mean, BRS has done this several times now. We're kind of most similar to the Vision Jet, of course. And like the Vision Jet, I expect that we'll program the flight control system to maneuver the aircraft into an optimal attitude for deployment, if we can. And if you can't, then you're just going to deploy it however.
Ken also asks, what is the range of prop rotational speeds? How does this change from helo to airplane mode?
So it uses a fixed RPM for both props at all times. The engine we have, in theory, has the capability to let us slow the prop by 10%. And I say in theory because we're still a little skeptical, and we're working with the engine manufacturer on really assessing if that's going to be true. The point of that slowdown is that helps us optimize the propeller design for the high-speed hover trade-off. So right now our design points are hot high hover, which is 100 degrees at 5,000 feet, 100 degrees Fahrenheit, 5,000 feet, hover out of ground effect. So that's one design point for the power, for the propeller and for the power from the engine. And then the other design point is that 353 knots at 15,000 feet on a standard day. And hover efficiency makes you want to have longer blades, which gives you supersonic tip issues at high speed. So those oppose each other. If we can slow the rotation speed in airplane mode at high speed, we can actually go with longer prop blades and get better hover performance. We don't need it. I mean, the prop design we have now works for both, but it would be nice to have a little bit of extra margin.
Peter, thank you. Personally, I'm fascinated by this, and I learned a lot this evening. And we're going to leave with one last question. So the question that we have is, when do you foresee full-scale aircraft testing to begin?
Not before Q4 2022. If everything went perfectly, we would have a full-scale aircraft starting to fly towards the end of 2022.
Well, thank you very much, Peter. That was a great presentation. I think all of us were intrigued by that, and I certainly learned a lot. And we'll all be definitely following Transcend Air as you guys continue your development. And I'm sure, you know, at some point we'll have you back again to give us an update. So that was great. Thank you very much.
Oh, my pleasure. Thank you, guys.
And just with regards to a couple other things I wanted to mention with the Aero Club in general. I started at the beginning by saying we were going to return to some in-person events. Our first in-person event will be starting on May 22nd with our first outing, which will be a gathering, either fly or drive to the Airfield Cafe in Nashua, New Hampshire. And we're also planning a fly-out event in June, July, and August, which, you know, the information on those will be forthcoming. Events that outings you can either fly or drive to, and those will be opportunities to also get together outside at various airport restaurant venues. So be on the lookout for those announcements. We're also going to have another virtual event in June, and the speaker will be Jim Baum, who's a member, and he's going to be talking about his experiences flying around the world in his TBM. And the date will be announced shortly. It's either going to be June 9th or 16th, but we're just finalizing that with the speaker, and we'll send out a notice on that shortly as well. So stay posted on that. Thank you guys all for joining us tonight. We appreciate it, and I hope you guys all have a great evening.